Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on Bessel functions. So in the previous lectures, we discussed how to calculate the Bessel function for integer indices, which was a simple integral. And then we said that if the parameter of the Bessel function is not an integer, then we have to also calculate another term, which was an infinite integral or an improper integral. And this representation for the case where the parameter of the Bessel function was a non-integer only worked for positive x numbers, right? And in general, if x is a complex number, only works for when the real part of the x is positive. That's just because of the convergence of this integral and the fact that the exponential either growing exponentially or decaying exponentially. And of course, as x goes to infinity or t goes to infinity here, we want to make sure that this integral converges to a number. And the requirement is that the real part of x be positive, or if x is a real number, it should be positive, all right? And also we saw that if alpha or the parameter of the Bessel function is not an integer, and then if x is negative, the value of the Bessel function actually becomes a complex number. It's not a real number anymore. That's another reason why this representation is not valid in that case. But what I would like to do here is actually go back to our calculations for the Bessel function for integer parameter and non-integer parameters and compare the accuracy with the implementation in other programming languages like Python. So the way I'm going to do it, I'm going to just calculate our Bessel functions in Java and export it into a text file, and then try to use a Jupyter notebook which runs on Python, and I'm going to compare the accuracy with the implementation that the Python has. And if you are not familiar with Python, Python has a package, scientific package called scipy. And in the scipy, there's a package called special, which holds all the special functions like Bessel functions and other type of special functions. So here, this is just a screenshot. So I use NumPy to handle my arrays, and then matplotlib.pyplot to do the plotting, because I want to plot the comparison between the values that I'm calculating in Java and the implementation in Python. And then in order to call the jn functions in scipy or in Python, I use the scipy.special. So we're using the special package in Python, all right? So let's head to Java. First, calculate our Bessel function. So in the test jn integration that we had before, let me see, I believe it was test number 1. And in the test number 1, let's from 0 to 50, let's calculate J0, J1, J2, and J3. J0, J1, J2, and there's 3. J1, J2, and J3, J1, J2, and J3. So I'm calculating from 0 to 50 in 1000 points for each of these functions, right? Remember, these are integers. And then we're going to plot them. And after plotting them, we're going to export them to Python. So blue, red, green, and black, K. J0, J1, J2, J3. All right, so let's run these. You see, it's pretty fast. So our implementation of Bessel functions for integer indices was relatively fast, all right? And you see, this is the result. Bessel 0 must start from 1. Bessel 1 must start from 0, and all the other Bessel functions, J2, Bessel 3, etc., they must start from 0, and they exhibit this oscillatory behavior, all right? So now let's export it to Python. In order to do that, I have this option, export to Python. And what this does is basically, in Python, basically it takes each XY plot in the figure and puts the data points in terms of a list in Python, right? So a list in Python is just a variable equals a square bracket open, a square bracket closed, And then you can have numbers separated by comma. All right. So here, so export to Python, let's call this jnvals. So this is just a text file, so save. I'm saving on my desktop, it's done. So now all these XY values for each plot is in the text file. So the next thing I'm going to do, I'm going to open up a terminal, and I have already installed Python and Jupyter Notebook, so I just call Jupyter, create a notebook for me. It creates a server, a Python server, and runs in my basically browser, opens up this server host, right? And then I'm going to create a Python 3 Jupyter Notebook on my desktop. All right. So what are we going to do? I want to handle some array operations, plot some stuff, and also use some of the special functions. So import numpy as np, import matplotlib.pyplot as plt, and note that I have already installed numpy matplotlib, and import scipy. I have already installed scipy.special as sp. Now, you know, if you are not familiar with Python, you see that Python allows this kind of aliasing. So these are called alias of packages, alias or alias import. What it means is that you can actually rename upon the importing a package, a class or whatever, you can rename it. And some people love it, some people hate it. So Java doesn't allow it. So you cannot have, when you import something, you cannot also create an alias for it. But the good thing here is that although it pollutes your namespace, so if someone uses some unconventional name for aliases, then if you look at their code and if it's a long code, you get quite lost of what is what, right? But there are some standard notations, like numpy is always abbreviated as np, matplotlib pyplot is always abbreviated as plt, a special package is always abbreviated as sp. I mean, these are just the conventions, and it's good to always follow the conventions. All right. So, okay. So now on my desktop, I have this text file, jnvals. So what I'm going to do, I'm going to open it in a text editor, and it's just a bunch of text values, x0, y0. And I'm going to hit Control A, select all of them, and then come here. So let's close this. And here I'm just going to paste them. And you see that it already puts them in a list representation, right? Now my x and y values, so x0, y0 is one plot, which one figure, which is j0. xy and x1 and y1 are the second figure, which is j1. x2, y2 is the other figure, x3. So in order to show you, I can plot them. So plt.plot x0, y0, and color, let's say blue. And I want to plot all of them. x1, y1, x2, y2, x3, and y3. All right. And let's also maybe red, green, and black. All right. As you can see, we have all these plots, and these are my imported values. So maybe let me also go full screen here. Okay. As you can see, the font size is a bit small. So what I'm going to see, I'm going to call plt rc params. So if you're not familiar with these, it doesn't matter. You can just look them up. And basically the parameters of the plot are saved in a dictionary or a hash map. In Python, we call map a dictionary. And the maps are just these curly braces, open, closed. And then I'm going to say, okay, font dot size, let's call it 15. Let's see if this works. So the font increases. I want to also increase the dimensions. So I'm going to say figure dot fig size. And I believe this requires a two-dimensional thing. So 16 and 9. Yes, it works. So, okay, now my figure is, so As you can see, we have J0, J1, J2, J3. So what I want to do is to compare these values that I calculated in Java, our Java implementation, compare the accuracy with the Python implementation, all right? So I'm going to take this and the color blue, and let's label this with Java, all right? And now I'm going to do exactly the same thing. Instead of y0, I'm going to call the special package. From that, I'm going to call jnew. And this jnew, if we look at the implementation, requires some arguments. The first argument is the index. So x0, y0, we already know that it's j0 and the x values. And these functions iterate over a list. So if I pass in the list, it automatically calculates the values for all the values in the list. Let's color this with red, and let's give it a dashed line style. Okay, and let's label it with Python. All right, as you can see, we're getting pretty much, and maybe also let's see PLT legend. All right, so the blue is Java, the dashed is Python, and as you can see, we get a fairly accurate result in terms of our Java implementation, which was relatively fast, but it's not the best implementation. And we still, when we compare it with the implementation in Python, it also gives a good result, right? Now the other ones are x1, y1, x1, and we pass in x1, but now x1, y1 correspond to the j1, so we have to increase the index. And again, as you can see, there is a very good match. x2, y2, x2, x2, and j2. Similarly, x3, y3, x3, x3, j3. All right? So that's how you can compare your result to make sure that the accuracy of our implementation is good enough. So there are always two things to do with these special functions, because there are different ways that we can implement them in any programming language, right? So far we have looked at the just straight up doing the numerical integration for integer and non-integer. But there are also other implementations, and Python most definitely is not using the integration. But we saw that for integer numbers, the integration is fast enough. So we're calculating 4 Bessel functions, 1000 points for each one, and it only takes about 156 milliseconds. So it's really doing a fast job. And we saw that the accuracy was also good. But what I want to do, I want to actually now change these to non-integer indices, 2.8, 3.9. all right? So disregard these labels for the moment. I just want to also look at the non-integer evaluations. As you can see, the non-integer evaluations take much longer time because they have to also calculate those improper integrals. So there are two terms. So let me just, but as you can see, all these Bessel functions, j.5, j1.7, etc., they all start from 0, which they should, and they eventually show this oscillatory behavior. So I'm going to export this in Python as well. Let's call this just test, and then open the text file, copy all the results, and then paste them in my Jupyter notebook here. All right, let's plot them. These are what I imported right now. And now x0, y0 corresponds to j.5. 0.5. And as you can see, it's still a pretty accurate calculation. x1, y1 corresponds to, I believe it was 1.7. So if I put 1.5, you see there's a difference. But if I put 1.7, you see there is a perfect match. So the accuracy of our calculation is good. x2, y2 corresponds to 2.8. As you can see, there is a very good match. And x3, y3 corresponds to, I believe, 3.9. Let's double check. Yes, it's 3.9 and we see a very good match. All right. So this is how we can basically compare our results with the other implementation. You can export to a text file and import it in Mathematica or MATLAB and compare your implementations. And so back to our PowerPoint. So this is how we're doing things. So here's the slide that I have, a comparison. These are for J0, J1, J2, J3, and J.7 and J3.88. all right. So note that in our in our Java implementation, integer J with integer parameter have a different implementation compared to J with non-integer parameters, because non-integer ones have an extra integration associated with them. All right. Okay, so to summarize for now, we looked at the Bessel function of the first kind, and this is actually the most important one, because other Bessel functions can in fact be written in terms of the values of this Bessel function. So the Bessel function of the first kind is very important, and therefore we have to ensure that we have a very good and efficient way of calculating it. All right. So we looked at the Jn and J alpha or J nu. So when the parameter of the Bessel function is integer or non-integer. And then we said that x for now we considered a real number, but now we want to also look at the complex numbers. So for integer index, the definition based on this proper integral that we had 1 over pi 0 to 2 pi cosine of x sine of theta minus n theta d theta. All right. This is still valid for all complex numbers x, and this is great because it's the same implementation. The caveat here is that now the cosine of a complex number is a complex number, and a complex number has a real part and imaginary parts. So basically what we need to do to calculate Jn when n is an integer number and x is now a complex number, what we need to do, we have to break this complex cosine function into the real part and imaginary part, and then integrate the real part separately and then the imaginary part also separately. All right. So what happens here is that I have this function Jn, this is my integral function, 1 over pi complex math. So I'm calling the cosine function from the complex math class that I have, and it takes a complex argument, calculates its cosine, and then returns a complex number which has a real part and imaginary part. So first I just take the real part and then integrate it from 0 to pi, and then I take the imaginary part and integrate the imaginary part from 0 to pi, and then the result is a complex number which is real part plus j imaginary part. All right. So this works for basically integer index, and we are lucky because in most of the physics and in engineering problems, the type of problems that we encountered, n or the parameter of the Bessel function turns out to be an integer value in most cases. So let's head to Eclipse. In my Bessel function integration, I have a Jn which has an int parameter and a complex x, and as we discussed before, we really don't need to have a very highly accurate integration method, so center rectangle should work fine here. Center rectangle. Similarly for the imaginary part, and we're going to do center rectangle. All right. And 0 to pi, what we're doing here, I'm using my complex math class which is in my mathlib project, and the cosine function takes a complex number and calculates a complex number based on the definition of a cosine function for complex numbers. All right. So we integrate the real part first and then the imaginary part and then combine them. So let's head here. Let's maybe create a test 5. And I'm going to call this public static void test 5. And what I'm going to do, I'm going to basically copy this one So I'm calculating from 0 to 50. So x is a real number. So let's delete all of these. Let's only take, for example, j0. But then what I want to do is to evaluate the j at a complex value. So new, so j becomes a complex number now, an array of complex number. I'm going to import it from mathlib library, new complex x.length, and then for int I equals 0, len equals x.length, I less than len, I plus plus. What we're going to do is going to j0 at I is basically Bessel dot jn int complex. So x, for x, obviously I'm not going to put this x because it's just calculates at real numbers. I want to calculate at complex numbers. So let's add a, so it takes the xi and add a j to it. All right, now this j, it doesn't recognize it because it's in our complex. So from our complex class, I'm going to import all the static parameters that we have. So it automatically imports j. So j here is just complex 0, 1. If you're more comfortable with I instead of j, you can implement it as I can't implement it as j. So basically what's happening here is that I'm calculating j0, all right? And let's remove these, just plot x and j0. So when I pass a x, and when I pass a complex number to plot it, it automatically breaks it and plots it as the real part versus x, imaginary part versus x, all right? So basically what happens here, we're calculating Bessel 0 at x plus j, and x is where x is a real number. But the input to the Bessel function is a complex number with a fixed imaginary part, all right? So let's invoke test5 to see what happens. 280 millisecond, and we're plotting both the real part. The blue one is the real part and the red one is the imaginary part, all right? And now we can export this to Python. Let's call this test2, for example, some name, and open it in a text file. Let's select all of these and go back in our Python. Let's remove these and paste the new values, shift enter to evaluate, and then we only have x0 and x1, right? The real part and imaginary part. So if I plot x0, y0, all right, so let's call this Java the real part, and then x0, but then I need to evaluate Bessel at 0, but the values that are input to the Bessel function are not x0, are x0 plus j. So I have to convert it to a NumPy array first and add a 1j to it. All right, and then we're plotting only the real part, and it's the warning that this function returns complex and it's throwing away the imaginary part. But we can avoid this warning by just calling the real function from the NumPy. So we're just plotting the real part. And as you can see, let's also call this Python re. As you can see, we get a perfect match. Now obviously we can also plot the imaginary parts. The imaginary part is x1, y1, x1, x1, and from NumPy we call the image function. And again, as you can see, we get a very good match, all right? So our implementation of calculating the Bessel function for integer index and a complex number is a good implementation. And again, Python doesn't do the integration. Python does something else, uses power series to evaluate the Bessel function, and that's what we're going to look at in the future. But for now, our implementation is good enough. All right, so back to our PowerPoint. So what happens if we try to evaluate the Bessel for non-integer indexes and a complex number? And again, the definition that we had for non-integer index is still valid even for complex numbers, but we have to ensure the convergence. And to ensure the convergence, then the x, if it's real, it should be positive. If it's complex, it should have a positive real part. All right, so must converge. Let's write it here. This integral must converge, right? And in order for it to converge, it depends on x, the sign of x, if it's real, or the sign of the real part of x, if x is complex. So this representation, the integral representation of the Bessel function for non-integer index, is only valid when the real part of x is positive. All right? So again, that means whatever code that we wrote for evaluating these integrals for the case that x is a real number, if x is complex, the code is pretty much the same, but we have to calculate it twice. One for the real part of these functions, then for the imaginary part of these real functions. All right? So we have to calculate the integrals twice, one for the real part, one for the imaginary part. And then we have to use also the complex definitions of the cosine function and exponential functions. All right, so you have to be careful about that. And again, here's the comparison. I'm calculating here Bessel 2 x plus j. In the example that I showed, that demonstrated, it was Bessel 0 x plus j. But here it's Bessel 2, j2 of x plus j. X is a real number, j is the complex number, and then the sum is a complex number. So we're taking the integer index Bessel, and then I'm calculating both for negative numbers and positive numbers, 1000 points. My complex numbers are x plus j, and I'm calculating Bessel 2. So this is what I get for the real and imaginary parts in Java, and then when you compare it to the implementation in Python, they give you a very good match. All right, so our implementation is accurate based on this integral definition for integer index, real or complex x doesn't matter, positive, negative doesn't matter. This, for integer number, this is the definition. You can always represent the jn for any number x, real part number, complex, positive, negative, doesn't matter, with this integral. All right. All right, I hope you enjoyed this lecture. From the next lecture, what we are going to do is switch our definition for Bessel functions from the exact integral to asymptotic power series, or asymptotic series, which are just power series. So x to some power, multiple terms, we sum them up. And the reason that we do asymptotic series, because those are much easier to calculate, or much efficient to calculate. And the caveat is that for power series, we have to divide it into different regions. For example, we can have a power series that represents the Bessel function when x is small. We can have a power series which is different now, which represents or approximates the value of the Bessel functions for when x is large, right? So we should switch between different power series based on how big or how small the x is, right? But again, power series are easier to evaluate, especially that when n becomes non-integer, we have to deal with that infinite integral, improper integral, and that really depends on how fast this exponential is decaying or growing, right? It has to decay. So, and the speed with which this exponential is decaying depends on the magnitude of x, or the real part of x. So the evaluation or the accuracy of this integral eventually becomes dependent on x. All right, thank you for watching, and I'll see you in the next one.